Today we're continuing with Chapter 16, Section 9, the second part, which is Cramer's rule. First part, we talked about solving systems of equations that had two equations and two variables. So we're still completing Algebra 2 Standard 2. The material in the black ink we did at the beginning of the year. Now we're revisiting solving systems of simultaneous equations only using matrices. And in today's objective is we're using Cramer's rule to solve a system of three equations and three variables. So let's start with our system of three equations and three variables, x, y, and z. We want to make sure that we have, when we start, all the x's lined up, all the y's lined up vertically, and all the z's lined up vertically. And then we have the constants, d, h, and l. We're using the letters to represent the constants in this particular situation. And I've color-coded them in blue because we're going to substitute them into the matrices in various positions just like we did with two equations and two variables. When we had two equations, two variables, we needed three matrices to get our answer, which was an xy ordered pair. Today, with three equations, three variables, we're going to need four matrices, and our answer is going to be an ordered triple, an x, a y, and z, which represents a point in three-dimensional space. So let's start by setting up the four matrices, and then we'll calculate their determinants. For the denominator, very much like what we did with 2 by 2 systems, we're going to take all the coefficients of x, which in this case is a, e, and I, put them in the first column. Take all the coefficients of y, b, f, and j, put them in the second column. Take all the coefficients of z, c, g, and k, put them in the third column. And that matrix, when we find its determinant, will represent the denominator of our ordered triple. For the determinant of the numerator of x, just like we did with two equations, two variables, we're going to replace the x coefficients, a, e, and I, with the constants, d, h, and l. So we're going to take the a, e, and I out of the first column, replace them with the constants, d, h, and l. For the numerator of y, we're going to take those y coefficients, which were in the second column, and replace them with the constants. So let's look at what they were. They were represented by b, f, and j, the y coefficients. We're going to replace them with the constants d, h, and l. So the second column, we're putting in the constants d, h, and l instead of the coefficients of y. For the numerator of z, we're going to do the similar process. We have the coefficients of x in the first column, coefficients of y in the second column. We would have had the coefficients of z in the third column, but we're going to take those coefficients of z, c, g, and k, and replace them with the constants d, h, and l. So we're taking that c, g, and k out, replacing them with d, h, and l. And if we simplify and find the determinant of each of these 3 by 3 matrices, we'll have our ordered triple in space, which will represent our solution to the system of simultaneous equations. How we do that, for the x component of our answer, we take the determinant we found representing the numerator of x, put it over the determinant of our denominator. For the y component of our answer, we take the determinant of the numerator of y divided by the determinant of the denominator. And for the z coefficient of our answer, we're going to take the determinant of the numerator of z divided by the determinant of our denominator. And that's how we'll put the pieces together to find our solution, the ordered triple in space. All right, let's look at a numerical example. Numbers always seem easier to work with. So here's our system of three equations, three variables. X minus 3y plus 7z equals 13. X plus y plus z equals 1. X minus 2y plus 3z equals 4. We've made sure that we've lined up all the x's together in a column, all the y's together above each other, and all the z's together. And then the constants, again, I'm color coding because we're going to substitute them in certain columns in our matrices. For the denominator, We're going to take all the coefficients of x, which are 1, 1, and 1, and put them in the first column. Then we're going to take all the coefficients of y, negative 3, 1, negative 2, and put them in the second column, negative 3, 1, negative 2. Take all the coefficients of z, 7, 1, and 3, put them in the third column, 7, 1, and 3. When we find the determinant of this matrix, that will be the denominator of our answer. So let's go ahead and do that. And let's use of the two methods that we've learned. We learned expansion by minors and we learned the definition. Let's use the definition mostly just because it fits in a smaller amount of space. To remind you of what that was, we take the first two columns, write them over again outside the matrix. Then we're going to look for all the diagonals going down from left to right containing three numbers. We're going to find their product and add that to the running total. So we're going to add 1 times 3, which is adding a 3. Then we're going to add negative 3 times 1, which is adding a negative 3. Next we're going to add 7 times 1 times negative 2, which is adding a negative 14. Now I recommend drawing these little diagonal lines because it's easy sometimes, if you don't space these columns evenly apart, to multiply by the wrong numbers, excuse me, and then your answers will not be correct. Alright, we're going to continue the process. We're going to take all the diagonals going up from left to right and we're going to subtract them. So we're going to subtract the product of 1 times 7. So we're subtracting a positive 7. Then we're going to subtract negative 2 times 1, subtracting a negative 2. And then we're going to subtract 3 times 1 times negative 3, which is subtracting a negative 9. Let's simplify the numbers now. So 3 plus negative 3 drop out to 0, plus negative 14 is negative 14. Negative 7, and don't forget you're subtracting negatives or adding. So negative 7 plus 2 plus 9 is 4. And negative 14 plus 4 is negative 10. Now I just did a little bit of a subtotal of the blue numbers and red numbers. You don't have to do that. You can just add them across from left to right if you wish. So again, the determinant of our denominator is negative 10. Let's begin with the determinant of the numerator of x. For that, if you remember the words in the game plan, we're going to take the coefficients of x, 1, 1, and 1, which were in the first column. We're going to replace them with the constants, 13, 1, and 4. So in the first column, we'll put in 13, 1, and 4 instead of the coefficients of x. We're going to repeat the process of finding the determinant. To do that, we're going to take the first two columns and write them over again outside the matrix. Again, we're going to look for all the diagonals going down from left to right. We're going to add their products. So we're going to add 13 times 1 times 3, which is a 39. Then we're going to add negative 3 times 1 times 4, which is a negative 12. Then we're going to add 7 times 1 times negative 2, which is a negative 14. We've run out of numbers that contain or diagonals that contain three numbers from left to right. So now we're going to consider the diagonals going up from left to right containing three numbers, and we're going to subtract their products, just like we did before. So we're going to subtract 4 times 1 times 7, which is subtracting a 28. Then we're going to subtract negative 2 times 1 times 13, which is subtracting a negative 26. We're going to subtract 3 times 1 times negative 3, which is subtracting a negative 9. Don't forget that all these subtracting negatives will become adding positives. 39 minus 12 minus 14 is 13. Negative 28 plus 26 plus 9 is 7. 13 plus 7 is 20. And we found the determinant of the numerator of x to be 20. Our next job is to find the determinant of the numerator of y. We're going to take the y coefficients, negative 3, 1, and negative 2, and replace them with the constants 13, 1, and 4. So the second column, which represented the y coefficients, we'll take the y coefficients -3, 1, -2 out, put the constants 13, 1, and 4 in their place. Again, we will find the determinant of this matrix. We'll do the definition method, so we're going to rewrite the first two columns. We're going to find the product of all the diagonals going down from left to right and add them together. So we're going to add 1 times 1 times 3, which is 3. Then we're going to add 13 times 1 times 1, which is 13. Then we're going to add 7 times 1 times 4, which is 28. There are no more diagonals going down containing 3 numbers. So of course that means it's time to subtract the diagonals, the products of the diagonals going up that contain 3 numbers. So we're going to subtract 1 times 1 times 7, which is subtracting a 7. We're going to subtract 4 times 1 times 1, which is subtracting a 4. We're going to subtract 3 times 1 times 13, which is a 39. Simplifying that, 3 plus 13 plus 28 is 44. -7 minus 4 minus 39 is -50. And 44 minus 50 is -6. So that leads us, we found the determinant of the denominator, determinant of the numerator of x, determinant of the numerator of y. It's now time to find the determinant of the numerator of z. For its matrix, again, remember that the first column represented the x coefficients, second column represented the y coefficients, third column represented the z coefficients. So let's review what they were. They were 7, 1, and 3. We're going to replace those with the constants 13, 1, and 4. So back in the matrix, what used to be the z column, we're going to put in the constants 13, 1, and 4. Let's find the determinant of the numerator of z. Rewrite the first two columns over again. We're going to add the product of all the diagonals going down from left to right containing 3 numbers. 1 times 1 times 4 is adding a 4. Then we're going to add -3 times 1 times 1. So that was adding a -3. Next, we're going to add 13 times 1 times -2, which is adding a -26. There are no more diagonals going down from left to right containing 3 numbers. So we're going to subtract the product of the diagonals going up from left to right. So we're going to subtract 1 times 1 times 13, which is subtracting a 13. We're going to subtract -2 times 1 times 1, so that's subtracting a -2. And we're going to subtract 4 times 1 times -3, which is subtracting a -12. Don't forget that all the subtracting negatives will become the same thing as adding positives. -4 minus 3 minus 26 is -25. -13 plus 2 plus 12 is 1. And -25 plus 1 is -24. So we've got all the components here. We have all the determinants. We just need to put them together to get our answer. The denominator is -10. Numerator of x is 20. Numerator of y is -6. Numerator of z is -24. So for x, we're going to put the numerator of x, which is 20, over the denominator, which was -10. And 20 divided by -10 is -2 for the x value. For y, the numerator of y was -6. We're going to put that over the denominator, which was -10, and reduce -6/10 to +3/5. And then we're going to find the z value. The numerator of z was -24. Denominator was still -10. That reduces to +12/5. So our answer is an ordered triple in space, in three-dimensional space. The x value is -2. The y value is 3/5. The z value is 12/5. which you can write as a mixed number or leave as an improper fraction. And that represents the x, y, and z coordinates of a point in three-dimensional space. And to review our vocabulary words, there is a solution. So we say this system is consistent. These three lines intersect at one point in space, so we say the system is independent. And that's how we solve a system of three equations and three variables using Cramer's rule.